So this is basically a new kind of approach. Instead of using k-means, we're going to do something like with hierarchies. And basically, this has actually got a really interesting advantage to it too. So I actually took this image and kind of broke it apart from the curriculum. The curriculum shows you like the clustering, but I'm going to say like pretend like these points, ignore the colors for now. We have a set of points, and you can imagine, for example, like, okay, I could probably say this is probably one group here, one group here, one group here. But there's also a little bit of like structure in this case too. Like clearly like these points are closer to each other, and these set of points are closer to each other than this point over here. So you can kind of imagine it's like, you know, these are probably more like each other than this point over here, even though they might belong to one group. And something right here is like maybe these points are more closely related to these points, but they're more closely related with each other than these points over here. So there's a kind of a hierarchy of like how related they are, okay? So what we can do is actually apply algorithms that would apply this part. And this is visualization that's from the curriculum, where essentially you can see a little bit of ranking where essentially these smaller circles represent, you know, more closely related parts. So you can see like E and F here, C and B, I and H, and J and K are more closely related than any other points with each other, right? But you can see that I and H and J and K are more related to each other than are to G. So you can kind of imagine this hierarchy of saying, you know, how closely related you are. So this is actually really great, is that if we can apply this clustering algorithm, we can actually do some really great visualizations. And remember, a lot of data is not, you know, two-dimensional or three-dimensional even. You know, most of the data is going to be higher dimensional. It's going to be kind of tough to visualize and be able to look and say, oh, clearly these groups are together. So one kind of cool thing about hierarchical clustering is we can make something called a dendrogram. So this is really useful for higher dimension. And this visualization right here is actually built off of this guy right here. And so you can kind of see there's already a hierarchy where there's more or less three groups, but they're more closely related to this guy. So you can kind of use this to take very high dimensional data and still see where those things are related to each other. And what's kind of nice too is that we don't actually have to choose ahead of time, like in k-means, in the k-means algorithm, we don't actually have to choose how many clusters we're looking for. Essentially, we just rank them together. We make a hierarchy of like what things are close together, and then as we get kind of further apart, and then we can decide how many clusters do we actually care about. So what you can do with the dendrogram, for example, is say, okay, this is kind of like all the data points collected. And you can imagine the closer you are in the bottom of this tree, the more related you are. So if you ever looked at like evolutionary, biological trees, right? Of kind of like, you know, how evolution kind of goes through, the things that are kind of like closer on the same branch are more related to each other, kind of the same idea here. So you can imagine that like J and K are very related to each other, but they're more related to G than they are to over D over here. Essentially, you have to kind of go around this whole thing over. And you can see, let's say J and K, then G and D. You can see J and K is more related to G versus D over here. So it kind of builds this hierarchy that's built in. And what's nice now is like, okay, let's say we just want, this is kind of like saying this is one whole group, which obviously isn't super useful when you're trying to do clustering, right? Like, well, yeah, it's one whole data set. So what you can do is like, well, I want two data sets. Well, what you do now, essentially, is you just go ahead and take and go ahead and cut, like you imagine like mentally cutting this line right here. And that will give you this branch over here, these set of points and these set of points. And you can kind of see is that if I imagine G, J, K, I, H, and A, B, C, D, E, F, you can see that's kind of what forms over here. And by basically making that simple cut right here, we now have two cuts, or two groups. You're like, it's like, okay, like, but I want the next, like, I want a little more, you know, detail. Like maybe you think there should be three groups. So what you can do next is say, okay, let me go down this tree and cut the next highest branch. In this case, you can see the next highest branch is going to be this guy right here. So we cut this guy, and now we actually have three different groups. And you basically can keep traveling down this tree and cut the, what's it called? The little branching part right here. And you can basically create new groups. So you can see if I cut this group, and this group, you have 1, 2, 3, and 4 groups. Okay. And you can see that there's a different hierarchy of saying like, you know, what things are most closely related to each other. Does that make sense? Okay, cool. So a really useful thing, especially when you can't simply just like look at the data like this in 2 dimensions. This works for even higher dimensions too. So kind of quick thing of going through, different types. So one thing to say is like, okay, we can build this up, but it's like, how do we build this? Like, how do we say things are close together? So the simplest one, which I'll tell you is not used. In fact, there's no way to implement this in scikit-learn directly. It's not built into scikit-learn. You could technically do it yourself, but scikit-learn doesn't even try, called single link. So single link basically says, okay, let's link, what's it called? Sorry, links basically to the closest points together in each cluster, which kind of makes sense, right? You basically say what points are closest to each other and you link them together. So you can see here is that, for example, we might label C and B very close together. And then, we might have these different groups. So let's say we have A, B, C, and D, E, F. And basically you say, okay, let's link these two groups together. So you find like these bigger groups. And you say, okay, what are the two closest points to each other? Well, C and D are the two closest points together versus like C and, let's say this is already a group, G. You say, okay, well, that means we should label these as one big group together. And basically just compare the closest points with each of those groups. So you would, for example, if you wanted to figure out the next linking, so pretend we already have, I'm trying to draw here, there we go. We have this group, and this group already formed. And we say, okay, let's compare, I'm gonna write this in like pink or something so it stands out. Let's say C and D are the closest ones together from these 2 points. For this group, maybe C and G are the most closest, right? So this is going to be closer. And then from this group, it's like, okay, well, we already have C and D, and this one's going to be like C, D, and H. Okay, so those are like the 2 closest points from those different groups. And say, oh, this is the smallest one, so we'll go ahead label this together. And that's how we determine if groups are close together or not. Does that make sense? Okay, so that's called single link. Now, there's a few issues with single link. One that basically tends to happen is that it tends to create these elongated, like kind of like clusters, kind of like these long kind of, like if you imagine if I were to kind of draw this out, the clusters tend to look a little more like, oblong, ellipses and stuff like this. And that's because basically it's always using the closest point. So this closest point tends to swallow up everything that's near it. And so you tend to end up having one very large cluster for all the points, and then maybe a couple other smaller clusters on the side. And this might not really be ideal of like what you're looking for. And in fact, this tends to be like not perform very well. So single link usually is kind of like not even used. But it's the most obvious one. Just look for the closest point. So it's like, okay, like that doesn't quite work out. What's another choice? Well, let's go the opposite. Let's just go with essentially saying, what's the farthest point away from it? So looking at the furthest point away and say, okay, let me grab that point and pull it in. And so the idea here is that you're judging it not on which is the closest point, you're judging on what are the 2 farthest points from each other. And that way you can kind of say, okay, like you're kind of balancing this part out. And so the same idea here, you judge on what things are closest by looking at the 2 farthest points. And if this group has the closest distance of the 2 farthest points, then that would be one group. Does that make sense? So essentially what you're kind of saying, what are the most different points between these groups? And but you're the most similar to each other, okay? Some issues with this though is that, well, not issue, but it tends to create more compact clusters, essentially because it's always using the furthest one. However, there's an issue with this. It tends to ignore other points that are actually really similar to the actual cluster. Because now we're judging on the furthest point away. It's kind of like if you have this, for example, like in G right here, if you have this point that's really far off from the rest of the group, that's going to be your determining factor on what groups you're most like with each other. And what's going to happen, you're probably not going to end up getting as many points that are actually similar to this original group. So there's some issues in that. It's like, okay, so we tried the closest point, the furthest point, or farthest point. What would be the next one? Pretty obviously said average link. Average link basically says, all right, do the same thing with complete, but we'll measure the average for each point to point. So you can imagine measure every point to the cluster and say whatever the average distance is and whatever the smallest average is, those are the 2 groups that we combine together. Okay. There's some issues with this one in that sense of like, like I think this would work relatively well, but one thing you can do obviously that you have to measure every single point with each other. So that can cause an issue. So this is where Ward comes in. Ward is actually the default in scikit-learn, if I remember this right. But basically what the idea here, and I'm not going to go through the full math, though the equation is here. I think the curriculum actually shows a similar equation, if not this exact one. But basically what happens is that we say, all right, instead of looking at all the points averaged over to every other point and see what the average distance is, we're going to take, all right, here's all the points in the cluster. Let's find the average like point amongst all the points in the cluster, and then compare the average distance or that average point with other average points of each cluster, and essentially say how far are those points from each other. So this is the mathematics of it, but I think that makes sense. where essentially what we're doing is saying, hey, where does this average point exist in this cluster? Say, let's say for G through K, and say, oh, the average point looks something like right here. Oops, I can't draw. There we go. Like this is the average point right here. Let's say this is the average point right here. It's like the average point right here. And we compare how far those distances essentially from each other versus actually trying to do this. There's a little more math than just saying just literally the average distance. You actually are comparing the distance sums, the sum squareds. So like basically it's a little bit different from literally taking the average of each individual point, but it has a little benefit in the sense that it's more representative of the actual cluster and it's relatively efficient compared to trying to look at every single point. Okay. Cool. Any questions on those different linkages?
So you said Ward is the default, you think?
Yeah, I believe Ward is the default, and it performs pretty well.
Okay, and so you would consider using one of the others if you felt like Word wasn't working very well?
There's actually even more, like maybe I can show you guys the documentation, but like there's even more options in just Ward. This is more like, and to be honest, this is more like the progression of like what logically makes sense. You might start with single link. If you were to like develop this algorithm completely on your own and say, okay, let me look at the two closest ones. Turns out this actually performs very poorly in actually making proper clusters. And they say, okay, let me try the opposite. Let me try furthest point. It's like it's all right, but it's still got some issues. And then average link would probably be like, okay, this is kind of the compromise between the two. And this, you can think of Ward as being like an enhanced average essentially. Like almost like a weighted average.
Okay, so Ward builds on those other ones. It's not like
Exactly.
we would have to choose among them. It's just to know that this is what Ward is benefiting from.
Right. Yeah.
All this
Because
knowledge.
I think if you go just at Ward, you're just like, where did this thing come from? Like this just seems kind of like arbitrary going through.
Right.
So,
and why is it called Ward? It sounds like a guy, not like average and complete, Okay.
Right. Yeah. These seem like, like logical, but there's other
like
options
math,
too. Yeah.
Okay.
There's other options to how you measure this distance, but this tends to be the default because it gives you good results and it's relatively efficient.
Okay. Thanks.
No problem. So kind of see what this example code is. We're just going to go ahead and check out these data sets. And this is the main guy right here, our cluster hierarchy. And we're going to do a dendrogram, Ward, and single. Note that dendrograms can't be made directly with scikit-learn. I have to use scipy in this case. So that's kind of like what's going on here. But we're going to just check out the iris data set and go ahead and check out that cluster. And so note that basically I'm creating this cluster, this agglomerative clustering. I can never say that. In this case, we're just going to look for 3 clustering and then look at the linkages Ward. And I believe if I look at this right here, I believe where's linkage? Oh yeah, linkages Ward right here. So you can see that there's, that's the default here. So I don't even have to put linkage Ward. So basically we're using scikit-learn's clustering algorithm right here. We're going to have to predict it. And then we can go to create this model. We can do the fit right here. I not that I put it twice. I don't actually know why I did it twice. Anyway. So we have this model that fit. Unfortunately, I can't draw the dendrogram directly with scikit-learn, so I actually had to draw it directly with scipy. And so if you do this now, you can see a little bit of this clustering. So this is the iris data, and you can see here the dendrogram here. And what's kind of nice, remember, the iris data set is 4-dimensional, right? So I can't plot out 4 dimensions easily. But you can kind of see here is that like by kind of cutting out these groups, you can more or less see there's really like 3 main groups here, right? And you can probably see is that these 2 groups in general are a little, or I'm sorry, not these 2 groups. These 2 groups tend to be a little more closely related in that way. And you can see there might even be little subgroups in this case where like maybe this is kind of like a subspecies, for example, of like this iris, or maybe there's some kind of like difference between these 2. So you can kind of see these clusters kind of form. These colors are not really the best thing. You probably could do a little bit better. scipy does do has a special thing called a Ward object. I don't think it's an object, I think it's just a function, but it's basically another thing. And I actually liked scipy's construction here. It's a little more obvious where essentially it's like, okay, we can see there's definitely this big old cluster here. And then these 2 clusters are very similar to each other. But it means that I have to break it into a scipy object. So unfortunately, it's not really built well into scikit-learn, but you can build it up if you wanted to. And there's other code that you can probably find that will take, results from these labels and stuff to build these dendrograms. Okay, cool. So anyway, kind of interesting code. But hopefully that kind of shows you a little bit, like, especially if you have many, many dimensions, you can already still build a little bit of clustering and get a feel for these parts. Some advantages. So some great advantages that we can visualize clustering with higher dimensional space. So we don't have to rely on the sense of like plotting it out and seeing what those clusters are. It allows us to kind of create these kind of like clusters with, simple tools that we have, or I guess our human brain, right, can't conceive past 3 dimensions. The hierarchy can give us more context to say, like, what groups are closer related. So you can imagine if you did like market segmentation, you might say, okay, these are different groups, but these 2 groups are more closely related than like this 3rd group over here, where k-means doesn't really have that ability, or other clustering algorithms that don't use hierarchy. You can't really say these groups are closely related. You'd have to essentially use something else to measure that distance or difference. So hierarchical clustering allows us to do that kind of stuff. So that means it's really great for already hierarchical relationships. So you can imagine if you wanted to group things, let's say like if you were looking at like properties of like an alligator, properties of a cat, properties of a dog, you probably would guess is that a dog and cat, because they're related to, being mammals, right? They'd have more similarities to something like, an alligator. So basically it does really, this performs really well on data that already has a hierarchy built in, where things are more closely related to others. You can imagine this, like, for example, I don't know, like in different cultures and stuff, like cultures that are in the same area tend to have kind of like similarities more than cultures that are further away from each other. This can also apply to like different, like groups where like you might have unexpected clusters. For example, I'm thinking back to like evolutionary biology, where you have something convergent evolution, where essentially the similar situations bring the same, attributes of animals, even though they're not genetically related and stuff like that. So you can find some interesting relationships that, and of course I'm using like, biology and stuff like that, but it goes beyond that for other data sets too. Okay. So some disadvantages, it's computationally expensive. So even though I said like do some efficiencies, it goes up by n squared. Basically, as you get more and more features, it's just going to go up by squared. And that comes to the fact that we just have to consider all the points. Like there's no other way other than like consider each point. And note that instead of looking at kind of like with k-means, where we can say, okay, move this over, we have to consider every single point and then say how are they how are they built on top of each other. So that ends up basically more complexity in the search space. Excuse me. Also, it's sensitive to noise and outliers. So I did noise / outliers, but I really mean just like noise in outliers. So if you have a point that's just kind of like just randomly outside, or like another outlier, it can be sensitive to that and might include it into its points. So you can imagine like that average is going to move closer to those outliers. So that's some big disadvantages here. So I know we're out of time, but I think I just want to mention is dbScan, and we'll maybe talk about this next time. But basically, if there is noise, dbScan does a great job of actually performing finding this noise and outlier. So think of things like, if there are, what's it called? Like financial transactions, if there's some attributes of like fraudulent act and stuff like that, you can keep that out. Or if there's noise where it's like, oh, like, there's just kind of random like collection of data where it just was kind of on the outskirts and we really shouldn't consider that as part of our data. dbScan actually does a really great job of identifying those parts. And you can actually see dbScan, these 2 optics in dbScan. You can see these black points right here. It identifies that these are in fact different, like these shouldn't be part of a group. Essentially, these are going to be considered noise or outliers. So this is not talked about in the curriculum, but I do think it's an important clustering algorithm since we're talking about clustering. So I'll save this though for next time. And then we'll go right into, pipelines right after that. Sound good? Okay, cool. So I'll go ahead and stop recording here.